My name is Sachin Chauhan, and in this video you are going to see the problems related to the operating systems. Hello friends, in this lecture we are going to solve the problem related to the Banker's algorithm. Actually, Banker's algorithm is a deadlock avoidance algorithm. You may heard the resource allocation graph algorithm, okay, where the instances and resources are given, and we can move the instances to the resources and resources to the instances directions, and we can find out if there is a cycle forming. If the cycle is forming, that means there is a deadlock, and if the cycle is not forming, that means there is not a possibility of deadlock at that current situation. But sometimes when we do allocate the resources to the system or to the processes, we can't use that resource allocation graph algorithm, so we need to use another technique to find the solution. So this technique is used, called as a deadlock avoidance algorithm or a Banker's algorithm. Actually, why it is called as a Banker's algorithm is that because this algorithm is used in a banking system to ensure that the bank never allocates its available cash such that it can no longer satisfy the need of all its customers. So this is the main reason, that's why Banker's algorithm is used in a banking systems. So what happens here, there are four matrices are taken: available, maximum, allocation and need, which can be calculated from either or. So actually this need matrix can be calculated from max minus allocation. The allocation matrix is subtracted from this max matrix, which gives us a need matrix, okay. And this the last, that is the available, is calculated by total number of allocation of one instances minus a given instance. Means if 10 instances are given of a the process or a task, and the number of allocation becomes 7, so 10 minus 7 becomes 3. That means 3 instances of A is remaining to satisfy another algorithm or another process. So mainly these four matrices are used: available, which gives us available instances; maximum, which includes the maximum number of requests used by a particular resource or a particular process. Means the maximum number of resource requests used by the particular process is given in your max matrix. Next one is allocation matrix. In allocation matrix, the number of instances of current resource is given to the particular process is shown, and in a need matrix, the number of extra requests of a particular resource instance shown by the process is given, okay. So simply, now what exactly happens in a Banker's algorithm? Banker's algorithm works for a resource allocation. We have already said that. So in a Banker's algorithm, there are two algorithms actually given. First one becomes a Safety algorithm, and second one becomes the resource allocation algorithm. In a Safety algorithm, what we need to do, we have to check for the current situation that is our system is safe with the current resources. Means can it satisfy the current processes or not. If it can satisfy, that means we can say that it is a safe state, and if it does not satisfy the current process request, we can say that it does not satisfy the current request, so it is unsafe state. If your algorithm or your particular process instance becomes in a safe state, that means you can handle another request. After that, you have to also satisfy the Safety algorithm. And if your current process says that your algorithm is in unsafe state, that means it may occur to a deadlock. There may be the chances of deadlock. Means if the current request cannot be satisfied by your processes, that means there is a maximum chances of deadlock, okay. So what Safety algorithm says that there are 4 steps with the Safety algorithm. First one is work, means another matrix which gets equals to the value of available, means the current available resource instances given to the work matrix. Finish is a matrix, again a vector, just a simple vector. Finish of I equals to false for every process. For I to n means there are number of processes, so number of processes becomes false to the finish of I. Now we have to find a particular instance of I such that finish matrix of I becomes false and need matrix of I becomes less than the value of work, that means the value of available. So generally both this becomes true for this particular request. Okay, then if no such I exists, you go to the step number 4, that is if finish of I becomes true for all the systems of I, that means your system is in safe state. If not, your system is in unsafe state. If this condition, both conditions becomes true, we move to the step number 3, that is work equals to work plus allocation, finish of I equals to 2 for that particular process. Then we move again to the second step number for another process to check out. Okay, so it's a simple algorithm. Fine. Now what exactly we are going to do? For the safety algorithm, what we are going to do, we need to check the particular algorithm like this. Okay, can you see the safety algorithm? We are going to work side by side with this process. Okay, can you see allocation, max, available, what we have said here? So just I am going to move this somewhat to the left so I can show you. Is it visible? Okay, yeah, it's visible. Yes, it's visible. Okay, so allocation matrix, maximum matrix, available matrix, and need matrix. Most of the time this allocation and maximum is given to you. Okay, with the help with the help of these two matrices we can find out the available value and need value. In an exam, for the exam point of view, most of these matrices are given to you directly. Okay, so what this example says that there are number of processes given 5, P0 to P4. Resource types are given 3, that is ABC. Okay, resource type instances are given, so we have already said that resource types are 3, so these 3 resources and their instances are 10, 5 and 7. Okay, so we already have said that from this material we can find out the value of available. It's very simple. So how to find the value of available? So the ABC are the resources. For the A, what we said that there are 10 instances are available. So how many number of instances we have allocated to resource A? We have to check that how many number of instances of resource A are allocated to processes. So check it, allocation matrix, check the number of instances 2, 3 and 2, that becomes total number instances 7. Okay, what we are having here 10, so 10 minus 7 remains 3, so there are 3 instances of resource A is currently available for you to satisfy any another request. Fine. Next one is again 5, 1 and 1, 2, so it remains again 3. Fine. Next one is 7, allocation of C resources 2 plus 1 plus 2 becomes 5, 7 minus 5 becomes 2. So available value of available is resource A has 3 instances, B has 3 instances, C has 2 instances currently available at your system. Now how to calculate need matrix? So this need matrix is calculated from a formula called as max minus allocation. It's simple formula called as max minus allocation. So value of max is given and value of allocation is also given. So 7, it's a matrix, so generally we can calculate it row by row. So 7 minus 0 remains 7, 5 minus 1 remains 4, 3 minus 0 remains 3. So like this. Like this, 4 minus 0, 4, 3 minus 0, 3, 3 minus 2, 2. So 3 minus 2 value 0. Okay, so this becomes a new need matrix. How we are calculating? From need equals to maximum minus allocation. Now what we need to do, or what our safety algorithm says that, check here. This is just only a common scenario. What our safety algorithms do, check here. Can you see it? Oh, I think there is a problem like this. Oh, yeah. Yeah, fine. So work equals to ABC, and what your question is asked, is the system safe for you or not? Okay, so now what your safety algorithm says that work equals to available. So value of work equals to available, that becomes 3 3 2 for the current instance. Again what it says, finish of I equals to false for all I. So I am going to write down finish of I is finish of 1, and finish of process P0 is false, process of P1 becomes false, process of P2 becomes false, process P3 becomes false, process P4 becomes false. For I equals to 1, sorry, 0 to, I can write here 4, yeah, 0 1 2 3 and 4, sorry. Okay, is it fine? Okay, fine. Let's do it again. So finish of I equals false. Now find an I such that both finish of I equals to false and need less than equals to work. So check out for the P0 process. Need is 7 4 3. Is it less than your work matrix 3 3 2? Is it less than? Means 7 is less than 3, 4 is less than 3, and 3 is less than 2. Is it possible? No. That means P0 cannot satisfy at current movement. P0 cannot be satisfied at current movement. So what we do, if no such process exists, we need to move to the step number 4. If finish of I true or false, it's not, actually it's false. That means we need to again move to the next one. Okay, so process P1, let's take the process P1. P1 has the value 1 2 2, which is less than your work value 3 3 2. It's less than your work value. Is it less? Let me continue with this, like, okay, fine. So 3 3 2, your process P1. What your process need is 1 2 2, less than your work 3 3 2. Is it true? Yes, it is true. It satisfies your current need. 1 less than 3, 2 less than 3, 2 less than equals to 2. It satisfies your current need. What your algorithm says, need less than equals to work. Yeah, need is less than equals to work. If this value becomes true, means if this condition becomes true, what we need to do, work equals to work plus allocation. Work equals to work plus allocation. The value of work is 332. The value of work is 332, and the value of work, value of allocation is 200. So we need to add that value here, 200. So our answer becomes 5 3 2. Means now the value of work becomes 5 3 2. Sorry, 5 3 and 2. 5 3 and 2. Okay. So now, and the value of finish of I, where is finish of I equals to true. That means finish of P1 is true. Okay, so next one, P1 gets satisfied. Next is P2, that is 600, but we have only instances 5 3 2. That means P2 cannot be satisfied at current moment. So we just move to the next process, that is P3, that is 0 1 1, less than equals to work, that is 5 3 2. Can it satisfy? It's actually 0. So can it be satisfied? Yeah, it can be satisfied. So we need to add the allocation of P3 here. Okay, and the allocation of P3 is 2 1 1. So we just releasing those resources, 2 1 1. Answer becomes 7 4 3. Answer becomes 7 4 and 3. Now move to the next process, that is P4. That is P4. Need of P4 is 4 3 1, less than equals to work matrix, that is 7 4 3. Is it true? Yes, it's a true value. That means we are going to allocate the resource allocation of process P4 to the value of work matrix, that is 0, 0, 2. So it gives you like this 7, 4, 5. Okay, fine. Now which process are remain? Process P0 is remaining and process P2 is remaining. Okay, so you can either solve anyone. I am just going to take the process P2, that is 6, 0, 0 less than equals to 7, 4, 5, that is the value of work matrix after adding the allocation of process P4. So can it satisfy? Yes, it can satisfy. So I am going to release the allocation of P2. Okay, so allocation of P2 is 3, 0, 2. It gives you 10, 4 and 7. It gives you 10, 4 and 7 as the value of work. Now just only process P0 is remaining. So the allocation value of process P0 is 0, 1, 0 and the need value of process P0 is 7, 4, 3. So check the value of process P0, that is 7, 4, 3 less than equals to the new value of work 10, 4 and 7. Is it true? Yes, it's true. So release the resources of P0, that is 0, 1, 0. So 0, 1, 0 becomes 10, becomes 5, 10, 5 and the value becomes 7 here. Value becomes 7 here. Okay, so 10, 5 and 7, which were actual instances 10, 5 and 7. That means currently the sequence of processes if we are going to execute is P1, P3, P4, P2 and P0. This is a sequence. If processes comes into this requests, it says that your system is in safe state. What it says that your system is in safe state. So it's just a simple one. I think you can have a look at it. Just a simple one. At last we just have to evaluate the 10, 5 and 7 and just the finish of P1. Finish of P1 equals to true. So after we have taken P3, it's satisfying. That means finish of P3 becomes true. After it takes P4 becomes 2, P2 becomes 2 and P0 becomes 2. So when we comes to your safety algorithm, it says that at this position find an I such that both finish of I equals to false, but there is no process currently in a finish array or in a finish vector which says that it's a false, because we have already satisfied this where we have made a finish of P1, P0 to P1 processes to true. Okay, that means there is no process in a finish matrix which says that it's false. This condition, if either of one condition becomes false, it moves to the step number 4, and step number 4 says that if finish of I equals to true for all I, then system is in safe state. That's why we have concluded here this sequence the process sequence P1, P3, P4, P2 and P0 becomes or gives you a safe state sequence. In previous lecture we have seen the safety algorithm of this particular topic, and now the second part of Banker's algorithm, that is resource request algorithm. Now what happens when we see that the particular processes or the particular instance of that particular process gets satisfied either in a form of safe state or in a form of unsafe state. In a previous example we have seen that that particular topic or particular example found out in a safe state. Now what happens at particular instance of time, any process can ask for any other resources. Means in an operating system any process can requires any kind of resources, so it puts a request. Okay, so in a resource request algorithm we have to check that if process generally find or produces a request which is less than available or not. Means if we have resources available at ourselves and the request generated by that particular process is less than the resources available to us, If that condition becomes true, then and then we can satisfy the particular request. If this condition gets false, we need to terminate that particular process, or we need to put that process into the queue until the resources gets available. If resources are available, that means the value of available is greater than the request, so we can move to the next process. What we need to do, we need to add the value of allocation with the request value. Before that, we need to do the particular request instances, we have to reduce it from the available resources, and we have to given those resources to where, to the allocated part of that particular process. Okay, if we have allocated that particular process the particular request resources, then we have to reduce those request resources from the need matrix, because now the need of that particular process is changed, because we have added the particular resources to that particular allocation algorithm. Okay, so it may confuse you sometimes, but when we see the example, it is really simple one. Okay, so what I do, this is a chart which we have seen in a previous example. Okay, I am going to change only the values here, that means it is easy to understand. Okay, if you haven't seen the previous video, please watch it. After that, you have to continue with this algorithm. Now what we have said, that request less than equals to available. Now currently, if I'm going to write it down here, if suppose process P1 is asking for the resources 102, suppose a process P1 is asking for the resources 1, 0 and 2, that means process P1 is asking for the resources 1, 0 and 2. 1, 0, 2 means that is this one becomes A, this becomes B and this becomes C. Fine. So the process P1 is asking for that. So what we need to do, check out request less than equals to available or not. Okay, so process, what it is asking, 102 is less than available or not. 332, yes, it's available. Okay, that means we need to move to the next step. What is it? Available equals to available minus request. So where is our available? Here it is. Okay, what request is 102, so I am going to reduce 102 from this process, so it gets to the 230. Now the updated value of available becomes 2, 3 and 0. Fine. Now what is the next one is allocation equals to allocation plus request. So allocation, when it's allocation here, an allocation of P1 process with which allocation plus request, and request is 102, because we have to add of 1 here of A instance, we have to add 0 here of B instance, we have to add C here of C instance of 2. So it gives you value 3, 0 and 2. It gives you value 3, 0 and 2. Okay, third is need equals to need of I minus request of I. Need of I is what? Request generated by P1 process. So need of P1 process minus the request. So P1 process 1, 1 minus 1 becomes 0, 0, 2 minus 0 becomes 2 and 2 minus 2 becomes 0 and 2 minus 2 becomes 0. So updated matrix, both these updated matrix like shows like. So the graph is like this after the previous value which we have seen in the previous papers. So now what after allocating the request of 102, after we have what we have did, we have allocated the request 102 with according to your resource allocation algorithm. Now we have to check with the safety algorithm, is it feasible or not. So process need of process P0, need of process P0 is less than available or not. What your safety algorithm says, this. Okay, so it's you have seen in previous video. So again check the previous video for this particular link or particular topic, and we just move fastly to the solution. So need of process P0 is less than available or not, that means less than work or not. Okay, so value of work is 230 because value of work is equals to the value of available at the starting position. So I'm going to write down here work, that is equals to available, that becomes ABC, value becomes 230. Okay, fine. Now here P0 process needs 743, means P0 process 743 less than equals to 230. Is it possible? No, it's not possible. So P0 cannot be executed. Next one, P1, what it requires? 2022 less than equals to 230. 0 less than 2, 2 less than 3, 2 less than 0. Possible? No, it's not possible. So change it. Now P2 remains 600 less than equals to 230. 6 less than 2, no, it's not. That means this cannot be possible. Next one is 011. P3 process requires 011 less than equals to value of available 230. Is it possible? Yes, it is possible. So we need to allocate the resources of process P3 to the available matrix, that means to the work matrix. So we are going to allocate the resources of P3 process, that is 211 of which process? P3 to the work matrix, gives you 3, 4 and 4. Okay, fine. Now next process is P3, next one is P4. P4 needs 4, 3, 1. P4 needs 4, 3, 1 less than equals to current value of work, that is 4, 4, 1. 4 less than equals to 4, 3 less than equals to 4, 1 less than equals to 4. Yes, it can satisfy. If it satisfies, we have to remove its allocated requests, okay, resources, and give to the work matrix. So we are going to allocate the value of P4, that is 0, 0, 2, gives you 3, 4, 4 with the P4 process. Okay, fine. Now the current value of work is this, and the process remaining is P0, P1 and P2. You can either satisfy anyone. Now for the P0 process 743 and the value of work is 443, it cannot be satisfied. For the P2 600, value is 443, that means it cannot satisfy. But here the 022, that is the P1 process, requires 022 less than equals to the value of work, that is 443. It can satisfy our need. So we have to remove the request of P1 and allocate it to the P4. So I am just going to write where I should write. Here I can write here work equals to currently ABC, that is 443. Okay, now this satisfies. So remove the resources of P1. So I am going to remove the resources of P1 302 and giving it to the work matrix, that is 5, 4 and 7. 5, 4 and 7. Fine, that means it can satisfy. This is satisfying, this is satisfying. Next one remaining are only two process remaining, that is P0 and P2. So you can solve anyone. Yeah, sure. Okay, so I am going to starting with P0 process 7, 4, 3 less than equals to current value of work is 7, 4, 5. 7, 4, 5. 7 less than 7, 4 less than 4, 3 less than equals to 5. Condition becomes true, that means it is going to satisfy. So we have to remove the resources P0, that is, and I'm going to allocate it to the. So what we have said that at lastly 600 is less than equals to current value 755. It satisfies our need. So we have to allocate the requests of P2, that is 302 to the work matrix. So I am going to add 302 to the work matrix, which gives you 10, 5, 7. Okay, so 10 was the value of your A instance, P was value of your B instance, and 7 was the value of your C instance. So this becomes okay. Okay, that means if we are going to solve the process like P3, P4, P1, P0 and P2 after requested by P1 to this 102, okay, your system is in safe state. because all the processes are satisfying your need. If any process is not going to satisfy your need, that means your algorithm is not in your safe state, so there may be the chance that deadlock can occur. Okay, now many of students ask me that, sir, is there only a particular safe sequence formed? No, there is no particular safe sequence formed. It depends on operating system, what process it takes into your system first. Is either by starting P3, if I am going to start with, suppose this any process from P0 to P4, there is this conditions like this, that's why I have solved it. But if any process can satisfy the need less than equals to your available, you can execute that particular process first. That means for the particular safe state, there may be multiple safe states generated in your by your algorithm. Okay, so this is not only a particular safe sequence, there may be another safe sequence can occur, which shows that your what we say, that your algorithm is in safe state or not. Okay, so you have to combine both videos to solve this particular problem. Thank you for your support. Keep sharing, keep subscribing, and tell others to do so. Hope you have enjoyed this video. Thank you a lot.